Okay. I think we're good now. So I'm going to run this through real quick again, just for the web, our virtual attendees.
Yeah. Iterative, it's all very
why didn't we add?
So the other thing I want you guys to notice too is these, we were flying about, we'll look at the extrinsics, but I think we were flying between 60 and 80 meters. And I would say those targets are probably as big or bigger than that board. So like, that's how tiny they look. So just think about how big you want to make your targets when you're actually putting things out. Those ones that are very faint on the pier, if you guys have gone onto the pier, those are really big targets and they're still really hard to see. So that's the other thing is we kind of like to fly up first for a test flight and then kind of put them out and see if we can see them before coming back to the office and then finding that out too late.
Yeah. That's where like you need to like add another
So after we click our GCPs, I usually like to do this step first, and then I add the numbering, and I have that, and I'll usually save an image or take a screenshot and say, okay, this is my number. Then I'll go to my GCP file, which I'm going to make. So that is where I saved it it's this UAS demo flight, this text file right here. And it basically, I have the GCP numbers and their corresponding X, Y, and Z locations. And it's just a simple comma delimited file. So I usually like to put some metadata in here. North Carolina State Plane, GCPs, just to kind of give me an idea of what's my datum, what are units. That file, it's in the intrinsics folder, and it's a text file. I think it's the only text file. So, you want to make sure, this is where it's handy to have them plotted out in space, and then you also have your picture, and you look down and you go, okay, 1 is this point, 2 is this point. It just makes it really handy, and I think that'll become really clear when we do our field demo tomorrow, because I spent 2 hours trying to figure this out yesterday, and I still struggle with it. So hopefully, we'll go get through that together.
You said put metadata in there. You mean in the name of it?
In the name. So, I mean, ideally, when building this toolbox, we could have, kind of had all the files linked together, but we wanted it so someone could, like, if they already were at step 3, they didn't have to redo step 1. Yeah. In your operational framework, I would probably start linking everything together. Like in GUI Bathy, we do that. Like, you can't use a grid with this extrinsics unless their coordinate systems match, that type of thing. But for this, we're just trying to keep it simple. So that's getting your UVD. Did everyone was able to get through that? Okay, cool. So this is actually solving it. So C is a single extrinsic solution. So this is going to take that initial camera shot, and now we're going to do that solution that Kate said. And so kind of as a big picture perspective, we do this for our single image on our UAS. If we had a multi-camera station, we would do this, we would do B and C for every single station, every single camera, I'm sorry. So you want to do this for every single camera. So for a UAS, we're just using one camera. And so we'll kind of go through that again. But so for C, if we look down here, again, we're going to go into the saving information. If everyone could add a 2 here, that way we won't overwrite the other one. That's just section 1 is just saving information. Section 2, this is where we're going to point to our intrinsics. So again, our intrinsics are part of that equation. So it's going to affect what our extrinsics are. So you want to make sure you're pointing to the right intrinsics. Now, the intrinsics, again, has to be the same exact camera with the same exact recording mode. A frequent error that we get that the toolbox breaks down is someone will use their UAS and take a video, and that video gives a 4,000 by 3,000 pixel image. And then when they do their intrinsics, they use the camera version, which gives a 5,000 by 6,000 pixel image. And the pixel sizes don't align, and it just breaks the toolbox. So that's kind of one error we get. So you want to make sure it's the same camera and same recording mode. So then we go into our GCP information. So we want to point into our UAS demo GCP UVD initial. So that is what we clicked earlier. So that's I saved it under a folder called initial values. So 2 is the one we actually clicked. This one is the one we're going to use for this example. So then we have our UVD path. Now we go for our XYZ path, which is that text file that's already in there. And then this is, again, just some metadata for our records. This is North Carolina State Plane, NAVD 88 in meters. And then we also we select the image that we did our calibration on. And this is mostly just so we can double check our errors and to see how bad everything is. Or how great everything is. And then this right here is the number of GCPs you would like to use. So we had 5 GCPs. Now, a lot of times, your first crack at it, it's going to look terrible. And it could be the incorrect heading. It could be a lot of different things. A lot of times, I get my GCPs mixed up, and I number them wrong. And so this is a really good tool to identify which is the bad GCP if you messed one up. So a lot of times, like, it won't work. And then if I turn off one of those GCPs, suddenly it works. And I'll find that was a bad, it was a typo or something like that. So we can play around with that as well. This is our initial guess. Again, this is probably where everyone's going to spend a lot of their time. It's really good to have a good ballpark estimate of the guess. I would say probably the most important one to get generally right is the azimuth and the tilt. Usually, if I have no idea where my cameras are, I pick one of the GCPs and I say minus 100 or 200 meters to back away from it, and that kind of gets it in the right ballpark. And again, this is our fixed flag. So as Rob was saying, if we really know our GCPs our survey of the camera is right, we can fix them. And so if we know it's right, we can hit a 1, and that would say, okay, our X, Y, and Z, we know that's 100% right. Now, this is another really good troubleshooting tool where you can kind of say, like, okay, I know there's no roll on this camera. Let's set it to 1. Or you can, again, like, say which one is, you can find out your bad guess. Like, if you turn this guess as a fixed and it's really off, then you know that one's probably not right. And so then we can just run it. So, again, put it as a 2 right here under ONAME. And then if we run it, I started you guys off with an amazing guess. So you can see that the reprojected is projected right back on our red. So that's an idea of our error. Yes?
Do you have to change the 2 anywhere else? Like
No, just that. It's just to save it as a different name. So we had a really good guess there. And so you can kind of assess your guess by that image that we just looked at, that the clicked aligned with the solution. We also, we have an error to our extrinsics. So we can kind of guess here. Every time someone has an issue, I always point to them to look at this first. Like, if these make sense. Like, if your swing is 180 degrees, meaning your camera's upside down, something's probably like, it's not working there. So you can actually get a really good solution, but get a swing of 180 degrees. And once you get to step D and G, your stuff's going to look really weird. So it's always really good to double check what your extrinsics actually are. And so all of these are, you know, generally make sense. We have our reprojected here. You know, I would say probably 20 centimeters is probably really good. You know, depending how far you are and things like that, you start to get into 10, 20 meters, probably something is off again. And so that's kind of, you know, and then it saves a file, this IOEO initial file. And I won't, since it for time, I'm going to kind of zip through this, but I invite you guys to play with this. Is you can kind of see like what would it look like with a bad solution, or so here I'll run it. So here's our really good solution. And so let's kind of look like, let's turn off 5 and 4. So we just have these GCPs in a line. So we can go here, remove 5 and 4. And so we can see like that gave us a really bad solution. And so you can kind of play around with it and see how things change. Oops, so that's gonna break. Nope, that's gonna break too. There we go. So now we can go back. Another thing that's kind of fun to play with is like, this is a UAS. So, you know, generally our locations aren't gonna be super known. So if we fix our cameras, X, Y, and Z, it doesn't look great. And so that being said, like it makes it look like if you breathe wrong, this is gonna be wrong, which isn't true. It's just like if you're super off. And I will say probably the second most mistake I make is I put northing first and easting second, and it should be switched. Because that's how my GPS gives me my coordinates. And so usually my azimuth's always wrong. But you know, you can kind of play, I don't know if 50 is going to break it or not, but so it went from 50 to 100, it still found it. So it's just a little sensitive, but I would say your azimuth is very important and your tilt. And so, so we'll move on for that one for time. And then we're going to go, I think we're going into image rectification, right?
Yeah.
Okay, so I think we're going to do SCP solution on this one as well. So we're actually going to skip D, and we're going to talk about what Kate was doing with the stabilization of the images. So this is actually E, so SCP selection. So these are those points that Kate said we're going to stabilize against. Now, again, they can be GCPs if they fit the criteria where it's either a really bright image against something dark or dark against something bright. They don't move. They're within the frame. And so I'm again ask you guys to do number 2 on this under the saving information, so we can play around with it. Again, we're going to put under section 2, we're going to put our first image under there, and we're going to use bright. So we can pick all of our targets are either bright or all of our targets are either dark. That's for this code. I've developed other codes that you can mix and match them, but for this one, it's one or the other. And so this is going to be very much like B, where all we're doing is clicking. We're not messing around with any solutions yet. So don't forget, put that 2 right here. And so it's going to be very similar where we're going to zoom in. And so we're actually, if you look here, I have radius 20 and threshold or thresh is 194. And so I'll explain what those are, but just remember those numbers because I'm going to forget them. So we want to zoom in. And then, so here, this is what we're going to use our stabilization point. Now, I'll be honest, this is a terrible stabilization point. You generally don't want one where waves could be breaking and introducing other white things that it could start to track and to start to follow. But this was what we got to work the best on this example data. But we can go into that more. So once I have a good click, it's very like the UVD one. It's going to ask for the number. So hit what? Yes, sir?
Real quick, is that a good stabilization point because it's the furthest one from the camera, or could you choose one closer to the camera?
It's important to get a good distribution, just like your GCPs. It's not as critical. This one was poor just because you can see there's not a lot of contrast. You want more contrast than that. And so now it's going to ask us for the movement radius. So if you zoomed in really close, like I did, hit home, and you'll zoom back out. And so you can see this is our radius. So when we're stabilizing and we go to the next frame, it's going to search this whole area and consider it for that thresholding. And so this is really big area, especially because we have waves hitting the water. So we want to try to tighten it up as much as we can. So we're going to hit 20. And you can see now it got really tiny. And so now we're just searching right on the pier. So this is kind of a judgment call versus how much your camera is actually moving. And then also kind of the brightness. So if you're happy with 20, you hit enter.
Happy means
How big the rectangle is. Yes, yeah. So this is the thresholding. So here we have our intensities, and we want to isolate it so we're just finding the brightest part. So if we look at our intensities, we kind of want it to focus on this dark area, because in MATLAB, white is a larger value. So if you just think about that, brighter, larger. So if we want to say, let's get rid of everything below, well, I know the number, 194. So you can see 100, it's considering a lot. But if we do 194, you can see it really found the little checkerboard that we had. Again, this isn't the best example. We'll go on to the next one, but we're happy with it. So we'll go to SCP2. And so again, I'm going to zoom and then hit enter. I'm going to click. This is number 2. So we want to zoom out. And then, so the radius I have specified that we already figured out was 50, and the threshold's 180. And so the idea is that, you know, you're going to pick one and it's going to be wrong. You're going to find out it doesn't work that well, or it'll drift in the next function, and you just have to, it's trial and error, unfortunately. So I'm going to go and do radius and 50. You can see this one is a little bit, it's clearer. We can see it better. There's much more change. We hit 180. You can see we're focused on it. Ideally, we'd want to be focused on the center of it, but this is good for now. And you can see, so this one actually is not an GCP that we had. This was just a feature. And so we hit enter right there. 3. And then we can zoom out. So the radius 50, threshold 170. Let's see, 170. So I will say another limitation this method has is, and which I think, you know, in next iterations, we probably will add new versions, is we're doing bright and dark. This day was cloudy, so it was pretty consistent. But if you have a partly cloudy day, sometimes that really affects things, and you start tracking other things. So I think, you know, in the future, we're probably going to be doing different ways. Also, but that's one reason we made this modular, is that you could go up to this point, and then if you want to develop your own tracking algorithm, you're welcome to. But just, yeah, that's just a caution. So 4. And let's do 50. So this one's like what it looks like if it's perfect. So, and then again, when you're done, it's like the UVD where you just click down here. And then it will save a folder, your SCP UVD initial. And then to try to, I think I took way too much time, so I'm just going to speed up through this next one. So that's kind of all the hard work that you did. The next step is to do F. And F is going to, basically it's just going to run through the algorithm. It's going to take your SCPs, it's going to load all your images and start doing the tracking. So I'm going to hit 2 right here, just so we save it differently. And so again, you're going to point it to your first frame, which you did your SCP calibration on. You're going to point it to your initial extrinsic solution you got from C. And then you're also going to point it to your SCP path. The other thing you're going to do is give an estimate to the elevation of the SCPs. This is going to help refine our solution. It doesn't have to be as accurate as a GCP, but it has to be in the general vicinity. And again, I think next iteration, we have code to not need this requirement, but the next iteration of the toolbox probably. But for now, this is how we're doing it. And then again, where it's going to find your images, you know, some more timing information. And this is just if your timing didn't match before. So we will hit enter, and essentially this is what it's doing is, so the red is actually what it's tracking with visually, and then the yellow is our reprojection back onto it to see how good our reprojection is. So this video went really fast because we don't have that many images, but it's really good to watch because ultimately, if you have a bad tracking, you'll see this guy, like if he'll catch a wave, he'll just start migrating this way over here. And you can probably do that yourself, playing with the SCP thresholds and things like that. We plot out an extrinsic plot to show. Again, this is a very short file, so it's a little hard to see, but you know something has gone very poorly if it starts to methodically just drift 5 to 10 meters because your UAS was probably a better hover than that. Or if you see something just kind of go off the rails, so it's a good check mark there. So, but ultimately what this is doing is it's calculating an extrinsic for every single one of your frames, and it's saving it in a structure that's going to load each one of your frames as well. So it's doing that extrinsic calculation we did over and over and over again. So let me close these out for you, Kate, and get you going.
Yeah, it's so hard. Yes, so this was the SCP seem to have a different than GCP. How do you get the values that they would run? Because the GCP you deal with that.
All you need to know for the SCP is the elevation. So if you have a good idea of what it could be, it doesn't have to be as precise. So like I knew that other SCP was like kind of by the one GCP and they were on the dune and they were both about 7 meters. So. No, I had a slide. I didn't even know I had a slide for this. Okay. Well, this is just real quick to go over. We don't have to go through it again, but just that this flow chart, it just explains that we have to do B and C for every single camera of a fixed station. And then, you know, E and F is just if you do UAS. So UAS is just the red path going down here. And then you can see fixed station. You repeat this camera calibration module, A, B, and C for each camera. Then you go down to D, and then you can actually skip all the way down there if your camera is fixed. If your camera is moving, you have to figure something out there.